Frequency domain analysis. Describing function analysis is basically in linear system, we call it frequency domain analysis. Just like in linear system, I think when we all study electrical engineering, normally there are two approaches to solving problem. One is to solve it using time domain. And when we do time domain, then the answer is always in terms of t. So we show the answer at t equal to 0, t equal to 1, t equal to 2, t equal to 3, where is the distance, where is the speed. So we draw the answer, we give the answer in terms of time. So that would be a time domain analysis. Depends on your application. There are some problem that is better solved in the frequency domain analysis. I think all electrical engineers have to learn frequency domain analysis. And the typical problem that have to be solved using frequency would be amplifier. And then we build amplifier or headphone or whatever and say, oh, the amplifier must have a gain that can range from maybe 20 hertz to 20 kilohertz because that is the frequency range of the human ear. All right, after beyond 20 kilohertz, then your amplifier is beyond what we can hear. So your 3 dB can be outside, must be within 20 kilohertz. Outside that, your amplifier, you don't need to, you can roll off the gain. Okay, so obviously in that case, it is more meaningful to design amplifiers using frequency domain. We talk about 20 kilohertz, 20 hertz, is not so applicable to talk about time domain. So describing function is the non-linear system, so to speak, the copycat version of the linear system frequency domain. What I mean by that, so let us imagine an experiment that all of us will have to do. You don't do this experiment. When you study electrical engineering, in one way or another, all of you definitely do the following experiment. When you were in year 1 or year 2 electrical engineering, somehow you will go to the lab, all right, and then all of us will do this experiment. You can't run away. Then they will give you a circuit or ask you to build a circuit, all right, which is a linear circuit, linear system. All right, when you're year 1 or year 2, the circuit you build could be an op-amp circuit, inverter, op-amp, a non-inverter op-amp, or transistor, doesn't matter. Some capacitor, some resistor is stick inside, then some amplifier, operational amplifier, some inverter gain, non-inverter gain, whatever, doesn't matter. So they'll ask you to build something, then they will give you a function generator, then they will ask you to input a sine wave. Then after that, at the output, they'll ask you to connect to an oscilloscope. Then they'll ask you to look at what appear on the oscilloscope. Then you see, since you put in a sine wave at the oscilloscope, you also get a sine wave. Then after that, they always ask you to do this. They'll ask you, take this gain, this amplitude, divide by this amplitude, then we call the gain of your amplifier. Yeah, then so you say, okay, my gain, so let's say I call it M1 of this amplifier. Take this sine wave amplitude, output sine wave amplitude, divide by input sine wave amplitude, then you get the gain M1. Then they should ask you to put this and this on the oscilloscope, and then you see there's a phase lag. They ask you to measure the phase lag, which means this one is behind this one by how many degree. So let's say it's some 5 degrees. So then you represent it as phi 1. Maybe this lags this by 30 degrees, 45 degrees, whatever. So, and then this, they will always ask you to set to some frequency. So maybe this is omega 1. No, this is omega 1. So at omega 1, you have this gain and this phase lag. Then they sure ask you to go and maybe increase the frequency to omega 2. So you will increase the frequency, so now it's faster. So go inside. So come out, you also will see same frequency, faster. Then they'll ask you to take this amplitude, divide by this amplitude. So, and this is at omega 2, so you got omega 2. You divide, right? You get M2. Then they ask you to see this on the oscilloscope. At the same time, also put these two on the oscilloscope. Then after that, compare the phase lag. Then you see, okay, they lag by phase 2. Hello, can y'all tell me, have y'all done this experiment before? Yes or no? Hello? Hey, can someone say something? Have y'all seen this experiment or done this experiment before? Hello? Hey, can y'all hear me or not? Hey, y'all keep on type in and say yes, yes, yes. Hey, don't type inside the chat. It's very hard for me to talk, right? Look at the chat. Just say yes, you know.
Yes, approve.
Thanks. Just say yes. Anyway, I also don't know who say yes. There are so many of you. I don't know the voice come from who, but at least, you know, okay. All right, let me just finish this. So maybe they'll ask you to do omega 3, then, you know, which is an even higher frequency. Then you go in, come out, you will get this, you know, even higher frequency. Then same thing, you measure this, divide by this, so you get at omega 3, you get M3, and then you get phi 3. Then they will always, if you do enough, then they always ask you to plot the graph. Then they say, okay, this is frequency, omega. Then after that, this is amplitude. Then they always like to do it in dB. So do it, dB is 20 log magnitude. So at omega 1, omega 2, omega 2, omega 3. So omega 1 is M1, then you take 20 log M1, so maybe you get a point here. Then omega 2, so you 20 log M2, you get another point here. Then 20 log M3, you get another point here. Let's say you have a lot of points, then they always ask you to join up the points. Then they always like to ask you, what is the 3 dB? Then you take here, then you drop by 3 dB. Then it's here. Then, okay, then you say, okay, from here to here is the 3 dB bandwidth. Hey, have you all seen this? Yes or no? Have you all done this?
Yes.
Yes, Prof.
Yes, Prof.
Yes, okay. So this 3 dB thing and this plot, you go and buy, I don't know what, microphone, you go and buy headphone, you go and buy all sorts of audio equipment. They always like to show you this. All right. Oh, your how good is your equipment, you know, where is a 3 dB point? They always like to show you this curve. All right. Then sometimes we also draw this like that. Instead of drawing in this way, we also like to draw this way. The real part versus the imaginary part. Real, imaginary, same thing. So means what? We always like to draw this point. Phi 1. So it's an angle. So you take a measurement. Normally this is a minus angle. So phi 1 maybe is minus 30 degrees. So you go and draw minus 30 degree. So you get phi 1. Then this gain, I don't know, maybe this gain is 3. So you go and draw 3 cm from here, you mark off. Oh, okay, then this would be your this point, which is omega 1. All right, then same this, then you see phi 2, maybe this is 100 degree, minus 100 degree. So you go and draw minus 100 degree. And this is phi 2. Then maybe M2 is 2. So you go and mark off 2 cm, so maybe it's here. And since it's omega 2, so you label it omega 2. Then maybe this is minus 200 degrees. So minus 200 degrees is a line here. All right, so from here to here is phi 3. Maybe M3 is 1, so you mark off 1 cm, so it's here. So this is omega 3. Then you join. All right, so basically this curve and this curve, they are the same curve. All right, this one depends on, they like to call it polar plot or Nyquist curve. It doesn't matter. This line, they like to call it Bode plot. So this is Bode plot. So we all do this before. Now, why I spend so much time to do all these things is because for describing function, we are going to copycat this whole experiment. We are going to be a copycat, give a copycat version of this whole experiment. Okay, now it's 6:50. Go for a break, come back at 7:05. I will stop the video now and then walk away, take a drink. I will start talking at 7:05. Okay, let us start. Can you hear me?
Yes, bro.
Okay. Okay, so now we have a copycat version. Imagine we go to the lab now. Okay, also have a system. Now, earlier on, we have a linear system, an amplifier or op-amp or something like that. Now we are supposed to deal with a non-linear system. So the simplest non-linear system that I can think of for you would be the sine function or something like that. So the on-off. That means what? When the input is positive, the output will be 1. When the input is negative, the output will be minus 1. Okay, so just like before, we have this system, non-linear system. So it's non-linear. Then, just like before, go and input a sine wave. So we input a sine wave. All right, at omega 1. Then input already. Then at the output, go and look at the oscilloscope. Now, can someone tell me what do you see on the oscilloscope? What will you see? Can someone say something? Hello, what will you see if I connect the output to the oscilloscope, if the input is a sine wave? Hey, it's a very easy answer. Can someone?
I prove a square wave.
Yes, a square wave. Okay, from here to here is positive, so the output will be 1. Then from here to here is negative, then the output will be minus 1. Okay, then we say we want to have a copycat version. The copycat version would be you take this sine wave amplitude divide by this sine wave amplitude and say that is the gain M1. All right, then we look. It's a square wave. So how? Never mind. We just approximate this square wave as a sine wave. How to approximate? I will teach you later on. So we pretend that we see a sine wave. Okay? And then take this sine wave, divide by this sine wave, then we get M1. That is good. Then after that, since you pretend to see a sine wave, even though you rarely see a square wave, you also compare the sine wave with this sine wave and say on the oscilloscope and say, you have a lag of phi 1. Then this is at omega 1. So like before, we will do omega 2. Then go inside, then you go inside. Then come out, you will see also a square wave, but at a higher frequency, omega 2. Then you still pretend that it is a sine wave. Either you pretend or you approximate it as a sine wave. Then take the amplitude, divide by this amplitude, then you get a gain of M2. All right, at omega 2. Then you look at the sine wave you pretend on the oscilloscope, compare with this sine wave, then you see, there's a phase lag of phi 2. So let's say, then we do one more, like, So this is an even higher frequency. So you get an even higher, faster. So you will get this. So you still compare. Then you get omega 3. So you get M3. This is M2. Then you got phi 3. So you copycat everything that you do for the linear system part. For the linear system, when you go to the lab, once you finish this experiment, you can go home already because you can draw the curve and everything is done. For the non-linear experiment, you cannot. How come? Because if you increase the amplitude, let's say this one is A1, this one is A2. Can someone tell me what will you see at the output for A2? Hey, say something quickly. Then you can finish early, then all go and eat dinner or go and sleep or go and watch a movie, got Batman in the cinema.
Prof, I
What?
think it's the same as A1.
Yes, the same, it's the same. So if it is the same, then it's the same square wave, then you can approximate it with the same sine wave, then you will take this amplitude, divide by this amplitude, then it will no longer be M1. It will be a different M. So cannot. So which means now you unlike the linear system, you can go home. You do already, because here, if this is A1, then you increase the amplitude to A2. The output here, the amplitude will also increase. And then if you take this, divide by this, you will still get M1. This is linear system. The easiest way to think of linear system is things are proportional. If you double the input, you double the output. If you make the input 3 times, the output will be also 3 times bigger. So you divide output by input, you will get the same gain. That's why you go home. It's not you do extra experiment, no use one. It's same answer, don't need to do. Whereas in non-linear system, you are going to get different gain. So you need to do. So you have to repeat the experiment for A2, then maybe A3, A4. So you repeat until when? Of course, that the answer lies on your application. Just like for linear system, you omega 1 range from what to what. If you are doing amplifier, maybe omega 1 is 20 hertz. Then you do omega all the way up to 20 kilohertz. That is the range that you're interested in. So you have to sweep omega from 20 hertz to 20 kilohertz. But the amplitude you don't have to change. Whereas for nonlinear, you not only have to change the amplitude, you also have to change the gain. So the gain depends on application. You may change the gain from 0.1 to 3 because your gain you require to cover this range for your particular application. So that is application dependent. So now you have to do. So assume we go and do. So I already do A1. So all these are A1. A1. I got this. So I go and draw something first. So I got A1. A1. So I will get M1 phi 1. So this is omega 1. So omega 2, M2 phi 2, omega 3, M3 phi 3. So I copy this down. Then I do omega for A2. So I have to do A2. Then you got M4 phi 4. In general, they'll be different for omega 1. Then M5 phi 5. Then M6. Then maybe you do one more, A3, so M757, M858, M959. Okay, so just like before, I can take this 1 point, 1 point, 1 point, draw 3 points. Just like I draw this 3 point. For here, I draw this 3 point, I get this 3 here, so I can do. So let's do. So let's do. So this is real. This is imaginary. So this maybe is this one here. Just like before, phi 1. Then this is M1. So we measure this is omega 1. All right. Then draw this. So I will get 1 point here. Then draw this. I get 1 point here. So this was before. I can join up the points. So I join up the points like that. So which means I join up these 3 points. Then I can draw these 3 points also. I don't know where. Maybe the 3 points is here, here, and here. So I draw, then I draw out the 3 points. This 3 point, the characteristic is it has amplitude A1. These 3 points, the amplitude is A2. So I label them. Then I join these 3 points. Maybe I get the point here, then point here, then point here. So I join them. The characteristic is A3. Obviously, there are 9 points here. I can also, depends on my application, it may be more convenient if I join the points like that. If I join the points like that, then I actually join the points here. Then I join the points like that. Then I join these 3 points. This 3 point, the characteristic is omega 2. If I join this 3 point, the characteristic is that it has the same omega 1. Then I join these 3 points, is these 3 points here. So it's omega 3. They get the same information, but depends on your application, which one is more convenient for you to solve problem. You want to join the 9 points like that, or like that. All right, to have the same A or the same omega. This is what we call describing function. All right, this piece of curve here is describing function, the plots of your describing function. Okay, so now let's go to the theory. Okay, so just now we in block diagram, this is what we have for the experiment. And this one, the nonlinear system, the example I have was I put in the relay or the sine function. All right, then the input for my experiment was actually a sine wave. So it's a sine wave that is the input. And in maths, sine wave is this. So this is this. All right, the output, sorry, this should be C, not W. So can you change it to C? So we saw that the output is a square wave. So since I draw this from here, should be positive. Here would be negative. All right. So this was the experiment. Then I said we are going to pretend that this square wave we are going to approximate as a sine wave. in electrical engineering, the standard way to approximate a square wave as a sine wave is to use Fourier series. I can't teach Fourier series anymore. You all learn it in maths, year 1, year 2. So to approximate this square wave with a sine wave, you have, which is like that, C is this C, all right, is the exact version, is a square wave. But it is going to be approximated by a sine wave, which is this one, is a sine wave. Sine wave can be written like that or like that. You just do trigonometry, you can convert from here to here. This is a sine wave. All right, this is a square wave. This is a sine wave. So there's a approximation sign here. And how do you get A1 and B1? You do this integration. This is Fourier series formula. I cannot teach it anymore. You take this C, you put inside here. And this C is this square wave. You put a square wave inside here, you integrate this, give you A1, you put the C inside here, you integrate this, you get B1. Then you stick it inside here, and here, this would be your sine wave. If you do trigo, you can convert it to magnitude and phase. So it is root of this A1 square, B1 square will give you M, and phi is arctangent A over B. So, and in electrical engineering, we like to write this. To do algebra, our way, we write it in phasor. We always write this as M phi. All right, then we can do algebra easily. This is our standard way of doing algebra for sine waves. So now, back to this block diagram. So this is a real system, but for us to do calculation, do algebra, we will do the approximation by the system on the right. Input is still a sine wave, so there's no change. The right-hand side now, instead of a square wave, is now approximated by a sine wave of M and phase phi. And we always like to write this M phi. And this one, we always like to write this as A, the phase is 0. So now this system here is approximated by this system with input A, phase 0, output amplitude M, phase phi. All right. The way to get M is to do your Fourier series formula, get A1, A, B1, and then convert to M and convert to phi. Then you can convert to our electrical engineering algebra phasor. So now this is now approximated by this system on the right side. So this is repeated. C, just be very clear. C is what? C is the square wave. Approximated by M, phi is what? Sine wave. How do we do this approximation? Is through using Fourier series to convert this square wave to this sine wave. Finally, what is describing function? Describing function is nothing but, in layman's term, is just a gain. It's nothing but a gain. So we write describing function. This is describing function. It's a gain. Since it's a sine wave, so how you get a gain? You take the output sine wave, divide by the input sine wave, you will have a gain. So output sine wave represented by M phi, input sine wave A0. So you just take M phi divided by A0. This is nothing but a gain. All right, so you can think of it as a gain. All right, if you like, you think of it as an AC gain. We all, electrical engineering, we have AC, DC. AC is sine wave, DC is steady state. No, not steady state, is DC, direct current. So alternating current is a sine wave. So it's a gain. It's just that it's a sine wave gain. So take output divided by input. Then you do algebra, this, you can get this. All right, this is just secondary school algebra, so I won't show anymore. So this would be the describing function formula. And just remember, what is describing function is nothing but a gain. Output sine wave divided by input sine wave, whereby the actual signal is a non-linear signal. It could be a square wave, it could be a triangle wave. As long as periodic, you can use Fourier series to approximate it as a sine wave. And then after that, use the sine wave approximation and divide the output by the input. You note that the input is always a sine wave. It's the output that is approximated. All right, the input is always a sine wave. It's the output that is approximated. Okay, so this would be how the theory goes. So now let us look at one example of how to get the describing function of the relay or the sine. All right, we call it relay, or we call it the sine function, or on-off control. Or on-off switch. It doesn't matter. It basically two level. Okay, as far as I'm concerned, they all mean the same thing. So how to get it? First of all, to get it, you have to draw the in this case, my relay or on-off control, when input is positive, output is M. All right, not 1. In general, we call it M. Then output negative is minus M. So the input to the relay is a sine wave. So I draw a sine wave. All right. Sine wave omega t. If this is omega t, the sine wave here would be 2 pi. Here is pi. From here to here, you go here, the output should be, this is omega t. From 0 to pi, it is positive, so it is M. From pi to 2 pi is negative, so it's 2M. Okay, so this would be, in my notation, this is my C. Okay, so now how to convert this square wave to a sine wave? We use Fourier series. So now Fourier series formula is this. We have to do this. Now, this is Fourier series property. You don't have to do this integration, because if you do this integration, it will give you 0. Why? Fourier series is proven mathematically that if the signal here is an odd function, A1 will be 0. So you only need to do the integration for B1. If you see here the C is a even function, then you don't have to do B1. B1, the integration will always be equal to 0. So this is an odd function, all right? I hope you know how to see what is an odd function and how to see an odd function or even function. All right. So just 1 minute. If you get something, this is an even function. You draw a horizontal line. This distance to this distance is always equal from this distance to this distance. Then everywhere this would be a even function. It's a mirror image about the y-axis. This is even. If you do this, then your B1 is always equal to 0. Don't go and waste your time integrating. This is an odd function. A sine wave is a standard odd function. You take a ruler, you pass through any point. This distance to this distance is always from this distance to this distance is always the same. So this is a simple test for a odd function. All right, these are secondary school maths. Then your A1 will be equals to 0. Don't need to do. So in this case, this is an odd function because symmetrical, you extend it, you will do it like that. Then you draw this, you will find that, oh, okay, it's odd. So A1 don't do. So you only do B1. Then there are some simple mathematics tricks. You integrate. The standard formula is given like that. You have to put C inside. So one standard trick you look is here the interval is 2 pi, from minus pi to pi. So interval 2 pi. You can always, if you are lazy, you can do an interval of pi, then you multiply by 2. The area integrate is finding area. The area will be the same. All right, you find half the area, then multiply by the 2. Or you can do half pi. Then you get this area, you multiply by 4, you get the same B1. So whichever is easier to do algebra with. So obviously here, what I've done is I take an interval of half pi. Then this is the area, I multiply by 4. Why I want to take half pi? Because from here to here, this is half pi. C is nothing but M. So this is C. I can also multiply by 2 and then take it from 0 to pi. It's fine, it's the same. All right, I will be not clever if I do from 0 to 2 pi, because C I will have to do from here to here plus M, then from here to here minus M. Then you got to break up the C into 2 integration parts. Then you just find work for yourself to do, because the final answer B1 is the same. So once you understand all this, you go and choose your integration interval so that it is the easiest for you to do algebra. Then you you get this answer. All right. So now, then what is describing function is just the output over input sine wave. So, or we just apply the formula here. It's just this. So since A is 0, so B1 divided by A. So what is B1? B1 is this, divided by A. So it's just this. All right. So this is the describing function. Now, describing function is a useful tool for us to find what we call sustained oscillation. In linear system, we are used to sustain oscillation when you have the two pole that's exactly on the j omega axis. We call it marginal stable, and you will find that the output is sine